This book, called Engineer's Notebook, came out in 1982. I got it from Radio Shack. It gives a simple intro to the CMOS TTL and linear ICs from that era. One of my favorites is the LM3914N, a dot bar display driver. I'm going to walk you through a project using a sensor based on a circuit diagram from this book. Even though this IC is over 40 years old, it's still widely used. You can easily find it on Amazon or AliExpress for around 50 cents each. I'm going to redraw the circuit diagram. Based on that, I'll set up the breadboard and proceed with the project. For the LM3914N, pins 2 and 4 are grounded, and pins 3 and 9 connect to VCC, which is 5 volts. Pins 6 and 7 are linked together, and a 1.2 kiloohm resistor goes to pin 8 with a 1 kiloohm resistor to ground. Pin 1 acts as the first LED output. Pins 10, 11, 12, all the way to 18 will connect to the cathodes of the 18 LEDs, and the anodes of the LEDs will connect to VCC, 5 volts. In number 5 is the analog signal input, and depending on how much you feed in, it shows that level across 10 steps of LEDs. Let me break down the basic working principle of the LM3914. To supply variable voltage to the signal input, I'm attaching a potentiometer, basically a volume knob on the breadboard. The voltage level coming into pin 5 determines how many of the 10 LEDs light up. It's super simple. In this experiment, VCC is 5 volts. If the input is 0 volts, no LEDs light up. At 5 volts, all 10 LEDs light up. At 2.5 volts, you get 5 LEDs. But in reality, there's a slight difference from the exact input values. I'm going to run a new experiment with the LM3914. It's going to measure light brightness and display it on 10 LEDs. We do need a hardware change there. We'll remove the potentiometer and add a CDS photoresistor. This component changes resistance depending on how bright the light is. When I bring the light closer to the CDS, you'll see it respond. The closer it gets, the more LEDs light up, and as the light moves away, fewer LEDs turn on. The oscilloscope next to it shows how the brightness is converted into voltage. I think it's totally fine to call the input going into pin 5 of the LM3914N an analog signal input. Let's run a second experiment with the LM3914. This time, we're measuring how close a magnet is using a Hall effect sensor, the SS495A1. The SS495A1 can detect when a magnet comes within a certain range. For this, we just need a simple breadboard modification, swap out the CDS for the Hall effect sensor. The Hall sensor detects the magnet's distance and feeds an analog signal into the LM3914. Now, the LM3914 handles showing the distance on those 10 LEDs. As you can see on the scope, when the magnet gets closer, the voltage drops. When the magnet moves away, the voltage rises. So fewer LEDs light up when the magnet is close, and more light up when it's farther. Hall effect sensors like this are also used in something we see every day, our car's ABS braking system. Let's run a third experiment with the LM3914. This time, we're using an IR sensor module to measure the distance to an object. You can buy one for under $1 on Amazon. The IR sensor works by emitting infrared light from an LED, which reflects off an object and is received by a photodiode. If the object's close, the received signal is stronger. If it's far, the signal is weaker. We need to grab the analog output from the IC's pin 5 using a jumper wire, since the module's 3-pin connector only provides power, ground, and digital output. Once we connect the jumper wire from the IR module to the LM3914's pin 5 input, we're ready to go. Now let's check it out in action. I'll use my hand as the object. As I bring it closer, the voltage level drops, and as I move it away, it rises. You can see that on the oscilloscope. This is actually used a lot in toy robots. Let's run the fourth experiment. We're using a thermistor resistor to display the temperature level on 10 LEDs. You can get this component for under 10 cents. In this experiment, we're using an NTC type. When the temperature goes up, the resistance goes down. When the temperature goes down, the resistance goes up. We connect the thermistor to pin 5 on the LM3914, and the voltage changes based on the resistance. As the temperature rises, fewer LEDs light up. When it cools, more LEDs light up. On the scope, you'll see the voltage change with temperature. The point of this component is, of course, a thermometer. You should go build an LED thermometer yourself. Let's run the fifth experiment. We're using a sound detection sensor module to show sound levels on 10 LEDs. You can get this sensor for under $1. Just connect the A0 analog output from the sensor module to pin 5 on the LM3914N. In this experiment, I've placed an external speaker right next to it. This video covered 5 experiments to get familiar with the LM3914N. Why not try building it yourself? And of course, add your own new ideas.